Hello, my name is David Vulakh. I am a senior at the Math, Science, and Technology Center at Paul Laurence Dunbar High School, and over the last 2 years I have been working under the mentorship of Dr. 𝓜𝓐𝓧-𝓜𝓘𝓝 of the Computer Science Department at UKY to apply parallel and distributed computing techniques to a class of mathematical problems called constraint satisfaction problems. Let's begin with a brief overview of this video. First, I will introduce some background information about the class of problems that I have been trying to solve and the algorithms that I have been applying to them. Next, I will describe my project's goal and the program I created to try to realize that goal. I will present data that I collected about this program's performance, discuss the implications of these data, and discuss possible next steps before acknowledging some of the many people who have helped me in this process. Constraint satisfaction problems are a class of mathematical problems that require elements of a set of values called the domain to be assigned to variables in a way that satisfies specific conditions. Two classic textbook examples are the 8 queens puzzle and Sudoku. In the 8 queens puzzle, 8 queens must be positioned on a chessboard so that no two queens attack each other. This is a constraint satisfaction problem, where the variables are the positions of the 8 queens, the domain of values is the 64 squares of the chessboard, and the constraint is that no two of the queens attack each other. Likewise, in Sudoku, the variables are the 81 cells of the grid, the domain of values is the integers from 1 through 9, and the constraints are that each row, column, and 3x3 box must contain each domain value exactly once. Constraint satisfaction problems are theoretically interesting to the research community, but they also have many practical applications. Many problems frequently encountered in the industrial settings, like scheduling, timetabling, and resource distribution, are constraint satisfaction problems. However, the general constraint satisfaction problem belongs to a class of computational tasks called NP-complete, which means that there is no known polynomial time algorithm to solve the general case constraint satisfaction problem. The specific constraint satisfaction problems that I have been trying to solve is that of finding Costas arrays. A Costas array of size m is an m by m matrix of ones and zeros such that there is exactly 1 1 in each row and column, and no 3 or 4 ones form a potentially degenerate parallelogram. Equivalently, there are no equal pairs of displacement vectors between distinct pairs of distinct elements. Since each of these matrices has exactly 1 1 in each row and column, it can be represented as a unique permutation of the integers from 1 through m, where the ith integer in the permutation is the position of the 1 in the ith column. Looking at the leftmost matrix on the screen, we can see that there is a parallelogram and a pair of equal displacement vectors. So this matrix is not a Costas array. The second matrix likewise has a degenerate parallelogram in which two of the vertices coincide and a pair of equal displacement vectors. So this matrix also is not a Costas array. The rightmost matrix, however, has no equal displacement vectors and no parallelograms, so it is in fact a Costas array. It is not generally known for all m whether there exists a Costas array of size m. The smallest size for which this is unknown is 32. The algorithm that I was applying to search for Costas arrays is called the max-min Ant System, and it is one of a class of heuristic algorithms based on the foraging behavior of ants. When an ant colony is foraging for food, initially ants search randomly. However, if an ant finds food, it returns to the nest, secreting a trail of pheromones or chemical scent markers to attract other ants. Other ants that encounter this path also follow it, adding their own pheromone. The shortest paths have the highest concentrations of pheromone, so that eventually most of the ants are drawn to a single optimal path to the food source. This idea can be applied to constraint satisfaction problems by representing the search space as a graph. Virtual processes called ants probabilistically traverse the graph, altering the properties that govern future ant behavior based on the quality of the path they construct. In this way, future generations of ants can consider the learned favorability of certain path elements when constructing new solutions. I parallelized the max-min Ant system in order to decrease the runtime by a constant factor. The standard measure for the quality of parallel algorithms is efficiency, a measure of how well the parallelization process conserves resources. If T0 is the runtime of the program with one thread, and T is the runtime of the parallel program with n threads, then the speedup S is T0 over T, simply the factor by which the parallel version is faster. Efficiency is S over N, speedup divided by the number of threads, or T0 over NT, an approximate measure of the fraction of total computational resources used across all threads of the parallel program that would have been used by the single-threaded program. Ideally, we want efficiency to be close to 1. If efficiency is close to 0, that means that the parallel program is worse than parallel independent runs of a single-threaded program. The goal of my project was to design a parallel ant colony program that can solve relatively small sizes of the Costas array problem while maintaining an efficiency of at least 0.5 that I could, after testing, apply to the search for Costas arrays of size 32. Ants traversing the graph incrementally and stochastically build paths representing permutations, at each step favoring components with higher learned favorability. Different ant colony algorithms associate the information of pheromones with different elements of the solutions. I modeled my pheromone association technique after the one typically used for the traveling salesman problem, since the relative order of permutation components that is more important in both problems than the exact position of a given value. For example, pheromone information would typically be associated with the learned favorability of following one element with another. However, by implementing a concurrently accessible map, I allow the parallel ant workers to associate pheromone information with arbitrary length paths of component sequences. In this way, an ant that has constructed, for example, the path 1, 3, 2, 4 will not only deposit pheromone on the connections 1, 3, 3, 2, and 2, 4, but it will deposit pheromone on all subsequences of the permutation. Then a future ant in position 4, 2, 1 will, when determining the learned favorability of inserting 3, consider not only the learned favorability of following 1 with an element 2 greater, but instead use the longest suffix that has been associated with some pheromone value. In this case, a suffix of length 2, associated with the learned favorability of following an element with one that is 1 greater, and then another one that is 1 less. This is a high-level schematic of the parallel program I wrote. There are two types of processes. The central process, which I have been calling the queen process, spawns the worker processes and maintains the shared construction graph structure. The worker ants, which actually traverse the graph looking for solutions, query the structure for pheromone information. The paths they build are used by the queen to periodically update the pheromone map. In this way, though the processes never directly communicate with each other, they are able to indirectly exchange information through the shared data structures to improve the quality of ant solutions over time. The metric that I originally described in my project goal, efficiency, is graphed for this parallel program in figure 7a. On the vertical axis is efficiency. On the horizontal axis, the number of processors n, and each color line represents a different problem size m, as shown in the legend in the upper right-hand corner. The lines themselves represent median e-values. The whiskers represent first and third quartiles. For the larger problem sizes, 13, 14, and 15, and processor counts, 200 and 250, the median efficiency remains stable at approximately 0.6. The stability of this result across 3 problem sizes and 2 large processor counts implies that the efficiency will remain at that fairly high value of 0.6 for larger problem sizes m and worker counts n. Notice that for smaller worker counts, such as 50 to 150, the program has efficiency greater than 1 for those same sizes m equals 13, 14, and 15. Though the efficiency quickly drops to nearly 0 for smaller problem sizes, this is not a negative result, since small problems do not have a sufficient volume of work to distribute to that number of processors. If a small problem size requires only 5 traversals of the graph to solve, there is nothing to be gained from having 250 ants simultaneously traversing the graph, since 245 of them accomplish nothing. But for those problem sizes where parallelization could feasibly occur, the parallel program has high efficiency. Figure 7b shows the percent runtime decrease that results from using the map-based pheromone association technique I described. On the vertical axis is the percent decrease. The horizontal axis and individual lines, again, represent different values of n and m, respectively. For n is greater than 1, the runtime decrease is, with one exception, positive. Further, it is approximately 30% for all three of m equals 14, 15, and 16 at n equals 250 processors. This stable runtime reduction shows that the new pheromone association techniques could be used to consistently reduce the runtime of ant systems solving constraint satisfaction problems. Relating these results to the original project goal, the Ant system successfully solves small Costas array problem sizes while maintaining an efficiency greater than 0.5, even for large processor counts. Further, the new pheromone association method is approximately 30% faster on average than the standard method, meaning that it could possibly be used to significantly reduce the runtime of MMAS searches on general constraint satisfaction problems. However, after approximately 6,000 total days of CPU time, the Ant system has not yet found a solution in the search for Costas arrays of size 32. Possible future research directions include creating a distributed Ant system. The current parallel model relies on low-cost shared memory and therefore only runs on one machine. To coordinate the work of remote processors, the ants must be able to exchange information without relying on a shared graph, since two machines that do not have low-cost shared memory cannot quickly exchange information through a shared data structure, and so some other information exchange mechanism must be developed. Additionally, the new map-based pheromone association technique should be tested on other problems to ensure that it generalizes beyond the Costas array problem, because even though there is nothing in it that is specific to the Costas array problem explicitly, it is possible that the Costas array problem belongs to some small subset of general constraint satisfaction problems that can effectively be optimized with this arbitrary length sequence. Finally, the m equals 32 search will continue. There are many people who have helped me in this research process and whom I would like to thank. First and foremost, I would like to thank my mentor, Dr. 𝓜𝓐𝓧-𝓜𝓘𝓝, for his guidance throughout this project. I would also like to thank the University of Kentucky Center for Computational Sciences for allowing me to use several of their many processor machines. Also, the Math, Science, and Technology Center and the Kentucky Young Researchers Program for making this research possible and providing funding. And my friends and family. I would not be here without them. Here are sources referenced in this presentation. If you have any questions, please contact me at david.vulakh@stu.fayette.kyschools.us. Thank you for watching.